Yes, today we are going to study Euclid's theorem, very important theorem of theory of numbers. It is about basic concept of division. If I divides 7 with 3, I count the table, 2, here 6, 1. As you know that this is dividend, this is divisor, this is quotient, and this is remainder. This is quotient, this is divisor, we say this B, and this is A, and this is equal to R. Therefore, I can write it as 7 is equal to 3 multiplied 2 plus 1. 3 2s are 6 plus 1 7. And what are these values? This is A, this is B, this is Q plus R. Actually, we are going to prove that this division, this is the division, true division. Okay, we are going to prove this. I can write this as this. Someone asked me question. Okay, I can also write 7 3 1 3 4 table. Using table 4, I can write this 7 as 3 multiply quotient 1 plus remainder 3 1s are 3 plus 4 7. I can write it as BQ plus R form. Okay, he says me, puts question that if you divide 7 minus 1 minus 3 plus, and actually for subtraction we change the sign here, doing the subtraction process. Here minus and plus, here 10 plus. Also, someone says me, if I count the table, this can also be write 7 is equal to 3 multiply minus 1 plus this 10, 7. When you minus this 3, subtract 10 from 3. So 3 goes from 10, 7 is equal to 7. And this also can be written in the form A plus BQ plus R form. And if I divide this, I count the table to 3, and here comes 9 plus minus 2 here. Okay. But we say that this division is only true when R, we stop the division process when R is less than B, R is less than B, or 0 or greater than 0. Okay, and these Q and R are unique. Now we read out the statement. Let A and B belongs to set of integers, as you know that plus 0, plus minus 1, 2, 3, these are integers. And one condition on B, that B must be positive, greater than 0. Then there exists unique Q and R such that Q can be written in this form and 0 is greater or equal to R and less than B. Now you can see here, if I take a set A here, taking all these if I divide this with 3 fours, then here come more negative value. So this remainder 4, okay, this remainder 1, this remainder here -4, here 1, here 4, here 10. Okay, I write here 1, 4, 10, up to so on. I can continue this process. What are these? These are remainders. From where I got? I got from here remainder. What is this equation was? A is equal to BQ plus R. If I took X here, I'm taking different quotients, so I took here X because I'm taking different quotients. So what will be R? R is equal to A minus B X. So all remainders are of the form this remainder, okay, this remainder, okay, these are, and this remainder. If I continue this process, remainders will all come here. Okay, now I took a subset of A, B set, a subset of A which contain only non-negative elements. When I am taking non-negative, so one thing you can note, 0 may or may be the member of B. Why? If I take 6 and divide 3, 3 2s are 6, 0 must be in this set of remainders. Okay, now come to the proof. Now I think you understand this. I take, let A be the set of integers of the form A minus bx, means all remainders set for all x belongs to integers. What I said, 0 may or may not be the element of A. Okay, I take B subset of A. B contains all non-negative integers of A. Even if I took here -3 and it comes -9 plus it becomes 16. This also be positive, maybe 0 and greater than 0. Now I suppose that in this portion R is the least element. I took an element R which is the least element of set B. Okay, I took R as a least element of set B. So R may be 0, R may be 0 if 0 belongs to B. Okay, in this case I shows you, set of remainders can contain R, and R is greater than 0 if 0 does not belongs to B, as we see in the division case of this, where least element is 1. Okay, it may be 2, it may be 3, it may be 4. It depends upon the values of divisors and dividend. Okay, now we can join these two and we can write here that R is greater or equal to 0. Remember this open side is greater side and this corner is less side. So 0 is less than 0 is less than r or equal to r, and r is greater or equal to 0. Okay, r is greater or equal to 0. Here we prove this value, as r belongs to b. So r is equal to a minus bq for some x is equal to q, as we know that b contains a minus bx form numbers. So if r is the member of b, so it will be of the form this, and if r is a particular number, then we have a particular quotient for that is q. Okay, as we write here, example 7 3 2 6 1. When r is equal to 1, then there must be a particular quotient q. We did not write here x, so we write here q. So we can write a, this comes here r plus bq. We can write it as, which implies a is equal to bq plus r. This portion is proved, but next, the important thing, we have to prove that r is less than b, this portion. Okay, this portion. Two cases, r is less than b, r is not less than b. Here only two cases. Now we study r is not less than b. Okay, we suppose r is not less than b. If r is not less than b, therefore r is greater or equal to b. If not less, then greater or equal to. Okay, so r minus b is equal to is less or equal to 0. Okay, b comes here. So as you know that r is equal to a minus bq, r is equal to a minus bq. So we can put here the value of r, a minus bq minus b is greater or equal to 0. So we can take common this b from these two terms. Q minus 1 is greater or equal to 0. As you see that this whole number is also of form a minus bx, a minus b, this is x. As you know that all numbers of the form a minus bx belongs to b. All numbers of this form belongs to a minus b, q minus 1 must belongs to b. If this value belongs to b, then this is equal to this. So r minus small b belongs to b, set b. So we see that if we subtract something from r, it is the member of b. But what say here, r is the least element of b. So what goes wrong? This is contradiction. We negate this we negate this truth. What is wrong? Our supposition is wrong. Okay, so if this is wrong, so this is true. Okay, if this is false, then this is truth. So R is less than B. If this is 1, this is 2. If we combine this 1 and 2, 0 is less than R is less than B. We prove this thing. Now only one thing remains: unique integers Q and R. So we can say here, now we are going to prove the uniqueness of this B and R. We say that, we suppose that they are not unique. In one case, we have BQ plus R, where 0 is less than R is less than B. And in other case, we have in this division, okay, these are not unique. We have other values of Q and R where 0 is less than R1 is less than B. If these two values are same, then these are same, then these sides are also equal. BQ plus R is equal to BQ1 plus R1. Take the values of Q at one side and this R1 minus R. Okay, take common B, Q1 minus Q, R1 minus R. Here I can write it just like this. Why? As you know that these are positive values, their difference must be positive. If this side is positive and B is given positive, then this must be positive, because this and this product of these two terms is positive, so this must be positive. Okay, so Q minus Q1. Okay, here I give you an example. 2 is equal to 10 into x. If this is small and this is greater, this value must be less than 1. This is 1 by 5, less than 1. Then these two values will be equal. Why? Because R1 and R both are less than B, then their difference R minus R, their difference must be less than B. Okay, if this is small and this is big value, this value must be less than 1. Okay, and non-negative value less than 1 is only 0. So Q minus Q1 is equal to 0. That is, Q is equal to Q1. So one thing is proved, that Q is unique, not different. Now, if I put this 0 in this equation 3, B into 0 is equal to R1 minus R. So R1 is equal to R. Okay, because R1 minus R is equal to 0. This is proved that R and Q and R are unique integers. This is not a difficult theorem. Just revise my lecture 2 times. This is very easy and conceptual, not difficult.